Hello, I am going to take you through the derivation of half-life in radioactivity. I'll just go through the definition in a just simple and straightforward way. Right. First thing, we have to find an expression for n, the number of particles that are radioactive and remain in the sample. We are going to find an expression for n in terms of T. N is the number of radioactive particles, and we also have T is time, and the activity is given as the N dt, which is the rate of decay. And you'll find that the rate of decay, the N dt, is a function of N, and there's a negative sign there just to show that the rate decreases with time. So the negative sign shows that there is a decrease of n with respect to time. So we have got negative dn dt equals to lambda n. The lambda is a constant of proportionality such that we put an equal sign from this sign. We're putting an equal sign, so we have to input a constant there. So I took the sign to the other side by multiplying by negative sign both sides. So I am taking out, this sign is now coming that side. Right. The n is now there. So it's dn, dn over n equals to lambda minus lambda dt. And then I'll integrate both sides such that I integrate dn over n equals to minus lambda integral of dt. There is my integral, both sides. Next, I find the integral of dn over n is the natural logarithm of n, and then equals to minus lambda t, and then a constant k. Right. From there, you'll find out that n is equal to my e to the negative lambda t plus k. This is the power there because I took antilogarithms of both sides with base e. So antilogarithm of ln n base e, this is actually n, and then antilogarithm base e is e to the power that. Now I can take this and express it in a different way. This is e to the power minus lambda t times e to the power k, that's logarithms. So you find it that I expressed each term with its base, e to the minus lambda t and e to the power k there, but e to the power k is also another constant that I'm just multiplying to that. So I made it an a, and then there's e to the power minus lambda t there. Next up, this is how the expression will look like after that. N equals to a e to the power minus lambda t. Alright. So to find the value of a, that constant, we apply initial conditions. Initial conditions, this n initially is equal to n naught, the original number of radioactive particles. Our t is 0 when we started. So n naught equals to a e to the power 0, because when t is 0, everything here is 0. So e to the power 0, we get e to the power 0 is 1. So e to the power 0 equals to 1 will give us a is equals to n naught, because this is 1, so a equals to n naught. There is it. This is how we get it. Now that we have a, which is n naught, and then we can use this equation to link the number of particles and the original particles in the sample with time. Lambda is called the decay constant. It's just a constant. Now half-life, remember we want to calculate the half-life, but half-life is the time that we require for the sample to decay to half its original mass or half its original number of radioactive samples. So we are going to take n to be half of n naught for us to achieve half-life, and then t, we're going to write it as t half. So this is how we are going to do it. N is half n naught, t, we're going to write it as t half. And then we've got half n naught, we are substituting n equals to half n naught there, equals to n naught, that n naught here, e to the power minus lambda t, the t is now t to the power half, so we put a t to the power, sorry, a t half there, not power. Right, you continue there. This is our expression, because this takes away that one, and then we remain with a half, e to the negative lambda t half. It's just the division. You divide both sides by n naught, and the n naught will take away that other one. Taking natural logarithms both sides, we are going to have ln half is equal to minus lambda t half. Remember, natural logarithm of e is actually going to remove that e, so we just have this as its antilog. Now the logarithm now is changed to 2. I'm going to show you why, because the negative has disappeared. So let's do it here. Logarithm of half is minus lambda t to the power to the lambda t half. So what do we do here? This negative goes that side, so that is minus ln half equals to lambda t half, and then ln half to the power minus 1 is lambda t half. Oh, this one is giving me a problem now. Right. So this is ln 2 over 1 because we're inverting, so it gives me ln 2 equals to lambda t half. So this is the expression that we have there. So after that, we just divide both sides by lambda. We're going to get t half is ln 2 over lambda. That is it. Finally, we can represent this on a graph and see what happens. As you can see, we can have an exponential decay function, because we said n is n naught e to the negative lambda t. So this tells us that when time is 0, n is n naught, so this is n naught there. Okay, as time goes, this function decays, so it goes down slowly, down, and keeps on going down in such a way that after each and every t half, we are going to reduce the sample to its half. So after a certain time t, which we call t half, or the half-life, we're going to remain with half of the sample. So after the further t half, we're going to get 2 t half, which leaves the sample at a quarter of its original sample. So further decay will cause it to decay to an eighth of the original sample after 3 t half, and so on and so on. So I want to show you how you can come up with a simple expression of finding out the fraction of the remaining sample that is left after any time. So I am going to use this graph because after t half, I'm going to remain with half of the sample. After another t half, I'm going to remain with half of half. After another half, half of half of half. So what I'm going to do here, I'm saying how many half-lives are there after time t. So I'm going to say half to the power the number of half-lives. So this is the number of half-lives, number of t halves. But how do you know the number of half-lives? The number of half-lives is the amount of time divided by the half-life itself. It will give us the number of half-lives, such that we are going to get the fraction that is remaining in the sample. So we can use this one to calculate the number of remaining particles after a certain time t, which is n equals to n naught half to the power number of half-lives, which I said is t over t half. The same can be done for mass. The same can be done for activity. This formula will help you to find the fraction of the remaining sample after a certain time t, based on the half-life of a sample. Thank you very much. Continue supporting, like the video. Stay blessed.